Hello and welcome. My name is Rui Hugman. I'll be giving a short series of lectures on an introduction to history matching and uncertainty quantification or analysis in the context of decision support groundwater modeling. I'm currently a researcher at NCGRT at Flinders, where I'm working as part of the Groundwater Modeling Decision Support Initiative, the GMDSI, an industry-funded project which aims to improve the contribution that groundwater modeling can make to environmental management and decision-making. These lectures are being recorded for the groundwater modeling topic of the groundwater hydrology degree at Flinders University. They are aimed at those who are new to the topic, so perhaps just starting out in the field of groundwater modeling, or who only have a rudimentary understanding of groundwater modeling. They are, of course, aimed at modelers or future modelers. However, given the introductory nature, they also may be useful for practitioners from other fields or people who are just merely interested in gaining a bit more understanding of what groundwater modelers do. It is quite challenging to condense all of these topics and concepts into a single hour or even a couple of hours of lectures. So my aim with these talks is rather to provide you with a broad flyover of the core concepts which you will need to comprehend, and then throughout the lecture I will provide links to other videos, documents and tutorials which delve into the concepts in much more detail. I highly recommend that you continue to expand your knowledge, in particular of the theory, by watching these other videos and go through the tutorials in order to learn how to apply these concepts in practice. At the end of the video, I will provide a suggested sequence of which of those, in particular the GMDSI tutorials, to go through, and hopefully this should provide you a starting point from where to actually learn how to apply these concepts in practice. Just a bit of housekeeping. Most of the links I will be providing are hosted on the GMDSI website. Here you will find a series of videos by John Doherty and others which delve into these same topics in a lot greater depth, as I've mentioned. Those recordings are significantly more comprehensive and provide a lot more detail, as well as more formal descriptions of the concepts that I'm going to introduce here. You can find links to all of these recordings on the GMDSI website at the link provided on the slide. On that same website, you will also find a copious amount of other information, with many documents discussing various aspects of groundwater modeling in a decision support context. Many of these revolve around history matching and uncertainty analysis, as well as associated topics such as appropriate model complexity. There are also a really useful series of reports demonstrating real-world cases, webinars on numerous topics, and, as I've mentioned, tutorials which demonstrate how to apply industry standard software. So to start off, let's consider for a moment why we build groundwater models, or any environmental model really. Usually reasons will fall broadly into one of these three general categories. The majority of real-world applied modeling will likely be to inform some decision by providing a prediction of the outcome of some management action. For example, if we pump from this well, will a nearby spring go dry? Or how much water do we need to pump to dewater a mine? Or will contamination reach a water supply well? And so on. Other purposes may be to understand what factors and processes control the behavior of a given system. These would tend to be more common in perhaps an academic setting, but may also be encountered in applied settings, especially in an exploratory phase. Arguably, these types of modeling are also to inform a decision, just one which perhaps hasn't been formally expressed yet. Usually with a bit of effort or minimal effort, they can be expressed as a model prediction. For example, will recharge be less than a certain value, or is a certain fault a barrier to flow, and so on. Lastly, modeling is often applied to explore the effects of interacting processes, perhaps more at a theoretical or conceptual level. Such models are usually synthetic or representations of highly controlled environments. The topics we're going to be discussing in these lectures focus on the first case, models used to assist in environmental management. Such models will usually represent some real-world groundwater system for which we need to make a prediction. To be useful in a risk-based decision support context, model predictions must be accompanied by an uncertainty interval. This requires quantification of how wrong a model prediction might be. Only in this way can managers take decisions aware of the risks of an unwanted outcome. It follows from this idea that the role of modeling is to make a prediction, not to simulate a system, and not only to make a prediction, but to quantify the uncertainty of that prediction. And of course, where possible, to attempt to reduce that uncertainty. This is what a history matching and uncertainty quantification workflow aims to accomplish. Groundwater models simulate complex systems which are impossible to characterize completely. Geological media are heterogeneous at every scale, which we can at best define probabilistically. Hydraulic properties can vary by orders of magnitude across comparatively short distances, with combinations of connected and disconnected features which can occur from very small or to very large scales. Even human intervention in the environment is really often, so often poorly known and even poorly documented. So processes and properties interact across different scales, across multiple dimensions, most of which are at best measurable at discrete times and locations. Therefore, the data which we have to characterize a subsurface is so scarce that we end up having to apply a lot of interpolation or conjecture to essentially guess what happened or what occurs between these discrete observations. Even measurements of things such as heads or flow, from which we infer things about the system, mostly represent point samples and are, of course, also subject to errors and uncertainty. Added to all of this, models are by definition simplifications of these systems, subject to limitations of scale, discretization, and so on. Model cells in which the partial differential equations are being solved are much larger scale than the representative elementary volume at which those equations are supposed to be being applied. As such, hydraulic properties in the model cell reflect upscaled or complex combinations of these parameters. Boundary conditions are inherently rather coarse simplifications of the physical processes which occur at the limits of our model, and the list goes on. So not only do we know little about the detail of any given system, but the little that we know often does not translate directly to values which in a numerical model may allow for a meaningful simulation of that system. If you would like to listen to a more in-depth review of these concepts, Catherine Moore and John Doherty present a nice summary in the GMDSI webinar on decision support modeling concepts, which you can find on the link shown on the slide. So, as a groundwater system can never be known exactly, nor can it be simulated exactly, it follows that an accurate model is an impossibility. At best, a range of models can be achieved which are potentially appropriate to simulate a given system. As stated, these models are inherently simplifications of the real-world system. To judge how well we have managed to simplify reality, model outputs can be compared to real-world data. If a model is unable to replicate observed system behavior, then it's quite unlikely it is going to be useful to make a prediction. However, if it is able to match system behavior, then it may be a useful predictor. This doesn't mean that it's a good predictor, merely that we can't rule out the possibility of a prediction made by such a model. Thus, that prediction is a possible future outcome of a management action. The process through which we obtain parameters which adequately represent the system is referred to as history matching. During history matching, model outputs are matched to measured field data by iteratively adjusting model inputs, or model parameters. In this context, we are posing the groundwater model as an inverse problem, where model outputs are known and the model inputs are unknown. Recall that in the forward problem, parameters such as hydraulic properties, recharge, etc. are specified. The model is run and the model calculates heads and fluxes. This is what you do anytime you build and run a groundwater model. However, as we mentioned earlier, data on things such as heads or flows are usually more readily available and more reliable than measurements of hydraulic properties. So in this context, we can invert the problem to use what we know, heads and flows, to find out what we don't know, parameters or hydraulic properties. So the aim of history matching is to identify a set of parameters that produce a satisfactory match with observations or field data or observations of the system behavior. Very roughly, this process requires identifying targets or which observations that we care about that we wish to try and fit with our model, running the model with some best guess parameters, so essentially solving the forward problem using a set of selected parameter values, comparing the model outputs to measured data, so assessing whether that fit is satisfactory using some metric, usually some statistical measure of of misfit, and if that is not satisfactory, adjusting the parameters again and repeating the process. In essence, this is what you would have done during assignment 2, in which you perhaps manually adjusted hydraulic conductivity and maybe recharge to match measured values of head with which you were provided. This is what is referred to as manual trial and error. Although it can be quite useful for a modeler to gain insight into the system that they are modeling, and perhaps a bit of intuitive sense of how outputs react to certain changes in parameters, over the course of this and the next lecture, you should hopefully learn why manual trial and error on its own is entirely inadequate when undertaking modeling for real-world problems. So just to take a small detour here, mostly to give you a bit of foreshadowing and to provide a bit of context for what we're going to be talking about next. In practice, automated parameter estimation methods are used instead of manual calibration. These allow the history matching process to be formalized and require that the modeler actually translate all of the many subjective decisions which they might take during which parameters to change by how much and so on into quantifiable metrics or quantifiable values. The mathematics behind these methods can be quite sophisticated, but fortunately there are widely available open source or free software which implements them, allowing us users to apply these methods without actually having to know all of the intricacies of the theory. Although I must say it does help if we do. By far the most widely used in our industry, codes in our industry, are the PEST and the PEST++ families of software. These are open source software and include a variety of tools and techniques and methods for assimilating data, as well as uncertainty analysis for environmental modeling. And most groundwater modeling graphical user interfaces will have some options or interface to use PEST. Depending on which graphical user interface you're using, these will have varying degrees of sophistication. The PEST and PEST++ codes undertake highly parameterized inversion of our environmental models. In doing so, they run a model many times. Before running a model, the software updates parameter values in model input files. After running a model, it reads the values that the model has recorded in output files, and it accomplishes all of this through instructions provided by the user in pre-prepared control file text files. Both PEST and the PEST++ can be used with any modeling software, as long as that software can be run from the command line and can read input from and write output to external files, normally ASCII or text files. Thus, they effectively are wrapped around the environmental modeling software, or in our case groundwater modeling software, and manage all of the assignment of parameter values as well as reading outputs and comparing those outputs to measured data or field data, subsequently deciding what new parameters to adjust and by how much, and carrying that out. So essentially automating much of the process that I just described in the previous slide. On the GMDSI website again, there is a video by John Doherty, the developer of PEST, which provides an overview of the software as well as some strategies to make the most of its use. You'll also find a webinar by Jeremy White and Mike Feenan, some of the developers of PEST++, in which they discuss the suite of software which is PEST++, as well as the use of PyEmu, which is a Python module that can be used to interface with PEST and PEST++ tools. Okay, so now back to the basics of history matching. In most cases, although perhaps not always, we will have observations for the site which we are modeling. These observations provide us some information on the disposition of pressure, flow, mass, and so on within our groundwater system. Most commonly perhaps are groundwater levels or heads measured from boreholes, and perhaps measurements of flow at points along a river or stream, which might inform us about the interaction between surface and groundwater. Other examples may include solute concentrations or temperature, which may be used to inform a transport model, information gained from geophysics, or even indirect measurements such as observations inferred from remote sensing. All these measurements provide a picture of the conditions of the site with varying degrees of resolution over both space and time. However, it's a pretty fuzzy picture. definitely not HD. Perhaps more like an old silent movie with most of the film missing. Of the observations at our disposal, those which are selected for comparison with the model simulated values during history matching are referred to as the history matching targets. The information contained in these targets constrains model parameters so that the model is forced to respond like the real-world system. As a rule of thumb, including multiple types of observation improves the amount of information which can be gained during history matching, in particular where these may inform combinations of parameters which are otherwise unidentifiable, such as, for example, a combination of head and flow observations to inform the ratio of recharge and transmissivity. Observations which are likely to inform parameters that affect a prediction of interest should be prioritized. So, for example, for contaminant transport model, ideally you want to have observations of both head and contaminant concentrations or other observations from which you can infer transport parameters. An often overlooked observation type are spatial and temporal differences between measured values. For example, in the transient models, including observations of the difference between heads at different times, so can often facilitate better estimation of parameters which control dynamic processes, such as storage parameters or recharge rates, than if only absolute values are included as history matching targets. In this way, even if it is hard to match the absolute values, the ability to capture information contained in the temporal signals is not lost. Another example are differences in observation values over space. Explicitly including observations of, for example, vertical head differences between different aquifer layers can often improve the estimation of parameters which control things such as vertical flow processes. Thus, cases in which the prediction of interest relies on vertical connectivity between layers will likely benefit from the information contained in observations of head differences between layers rather than simply the absolute values of heads in each of these layers. On a side note, not many groundwater model graphical user interfaces, so GUIs, provide options to configure these types of more creative observations. Often it'll be necessary for a modeler to calculate secondary observations themselves. In an automated parameter estimation context, this requires additional software or scripts that automate the post-processing of model outputs into these secondary observations. Of course, the modeler can write the software themselves, and given the highly variable context in which modeling or groundwater modeling is often applied, this is by far the most versatile solution. So any groundwater modeler who has skills in software development or writing their own code, whether it be Python or Fortran or other, will always have a leg up. Alternatively, PEST has a suite of utility software which can be used to implement common post-processing steps. For example, you can find a tutorial on one of the GMDSI on one of these at the GMDSI website, demonstrating the use of the OL proc utility to post-process ModFlow 6 observation time series. Other utilities are documented in Part 2 of the PEST manual, which you can find on the PEST website. Now, any observation is inherently uncertain. Some may be relatively precise, whilst others may be little better than guesswork. All observations include measurement error. This is an error associated with the accuracy of the device or the method used during measuring. So, for example, when taking a water level measurement, inaccuracies in the tape measure and the survey of the measuring point, potential user error, etc. All of these compound to add a level of error or uncertainty to a measurement. Apart from the inherent uncertainty of the measurement, there are also errors introduced when comparing it to a model-generated value. Once again, issues of scale can come into play. Again, using heads as an example, if the location of an observation does not coincide with a model node, then model simulated values may need to be interpolated for comparison. Interpolation is an approximation, thus it has an inherent associated error as well. Or perhaps more intuitively, if a well from which heads are measured has a screen which only partially penetrates the thickness of a model layer, so the model simulated values and the measured values actually mean slightly different things. Thus, not only do the measurements themselves include uncertainty, but the comparison between measured and simulated values includes additional structural error due to the inherently simplified nature of a model attempting to replicate conditions in the real world. In an ideal world, we would like to quantify this uncertainty. In practice, it is not feasible. In principle, measurement errors can be determined by accounting for the precision of the devices and methods, but that being said, in most cases this type of information is not readily available. Added to this, quantifying the structural error inherent in translating model outputs to real-world values up front is quite challenging. Thus, total combined errors are always imperfectly known. In practice, target uncertainty is usually assumed based on a modeler's subjective estimate of the measurement error, and thus representing the uncertainty of the target observation, assuming a perfect model. History matching is usually implemented through minimizing a so-called objective function. The objective function can be defined in many ways. Perhaps the most common is the sum of squared weighted differences, or residuals, between model outputs and field measurements. Residuals are the difference between measured observations and the corresponding model outputs. For example, the difference between heads collected at a well and the simulated value of head at the corresponding location in a model. Weights are applied to this residual to increase or decrease the contribution of individual observations to the total objective function. Ideally, weights are assigned to give greater relevance to observations that have less noise or are less uncertain. In practice, weighting strategies usually need to be a bit more nuanced and will often reflect a quantitative measure of a modeler's judgment as to which observations are most relevant to inform parameters that affect the prediction of interest. Weighted residuals are squared so that all values become positive. This avoids negative and positive residuals effectively annulling each other when they are summed together. So residuals are calculated, multiplied by a weight to adjust their relative contributions, then squared to make all residuals positive. Finally, all residuals are summed to determine the total value of the objective function. History matching is achieved by minimizing the value of this objective function. From the equation on the slide, it is evident that the objective function will be dependent on the selected weighting scheme. There are no set rules for weighting, as what is important will vary depending on the modeling purpose and will tend to be a somewhat subjective and case-specific modeler decision. So as we've said, history matching aims to identify parameters for which model-generated outputs match field measurements. It is accomplished by iteratively changing parameters and searching for those which result in a lower objective function, so that minimize the objective function. Deciding that the objective function has been lowered to a value that is good enough is not straightforward, as good enough will always be subjective and context-specific. You may come across some suggestion for minimum values of some summary statistics like the root mean square error and so on. However, there's no reasoning that supports that meeting these types of criteria define a model with a good fit. At best, it might be reasonable to say that the minimum value of an objective function can be equivalent to the uncertainty in the measurement data. Effectively, it's pointless to try and improve a fit between a model output and a measured value beyond the precision of the measurement. In practice, this is unlikely to ever be the case, as structural error usually dominates the misfit. The subjective decision of whether a good enough fit has been achieved is often based on the modeler's expert knowledge. Key aspects to consider are whether any system behavior that is directly correlated to the prediction is well represented, and whether the obtained parameter distributions are still sensible. The translation of real-world parameters to a model requires assigning parameter values to every single cell in that model. These can include any model input, such as hydraulic properties, like hydraulic conductivity, storage parameters, recharge, values of boundary conditions, and so on. And as previously discussed, these parameter values in the model cell actually represent some upscaled average of the real-world system properties and processes. Because natural systems are so complex and observations of these systems are few and far between, history matching is said to be underdetermined. In reality, there are many more unknown parameters than there are known observations. So if we have a model that reflects the complexity and heterogeneity of reality, in our inverse problem, we have many more unknowns than knowns. This is what is called an ill-posed problem, and why groundwater models are fundamentally non-unique, meaning that there are many combinations of parameters, all of which may explain observed data equally well. and therefore can never be uniquely estimated based on field measurements of state alone. A well-posed problem is one that has a single unique solution. So there is one single best set of parameters which best explains the data. Obtaining a unique solution which best explains field data is referred to as calibration. It's worth noting that calibration and history matching mean different things. Calibration implies the search for a single unique set of parameters which best explains the data, whilst history matching is broader in the sense that it refers to any set of parameters which achieves an acceptable fit with data. So calibration can only be achieved in a well-posed inverse problem, but given what we've said so far, calibrating a groundwater model should not be possible. And it isn't, unless we employ some trickery. There is a comprehensive video by John Doherty discussing this topic on the GMDSI website. I recommend you watch it. Now, before we discuss this trickery, it may be useful first to define calibration and where it fits in relation to history matching. Bayes' theorem provides a formal expression of the concept of history matching in which we can embrace the non-uniqueness of a groundwater model. Now, don't be scared by this formula. The idea it expresses is quite simple, but quite elegant. Bayes' theorem describes the probability of an event occurring based on a previous event having occurred. In simple terms, it states that an initial belief plus new evidence leads to a new and improved belief. A prior probability represents that which is known or believed about, or which we know or believe about a system before we confront this belief with data. In a groundwater modeling context, this usually represents expert knowledge and site characterization, things such as what are reasonable ranges of values for hydraulic properties and or relationships between parameters at a given site. As you can imagine, in a groundwater modeling context, the prior probability distribution can often be quite large. We know very little about what happens under the ground. We may have upper and lower bounds to describe what may not exist underground. We may even have some point measurements of some properties or have a variogram that describes how they are likely to be distributed in space or time. However, the range of what we don't know is usually pretty large. Nevertheless, we can still notionally characterize a parameter probability distribution based purely on our prior information. This prior parameter probability distribution represents all the possible values and combinations of parameter values which may exist at our site. If we sample this prior and use that sample to run a model to simulate a prediction, we obtain a sample of the prediction prior probability distribution. By repeating that process enough times, we can obtain a representative sample of the prediction's prior probability distribution, or essentially a range of what may happen given what we know about given our prior knowledge of our site. However, as I've said a few times now, prior uncertainty may be quite large, which may in turn compromise the usefulness of modeling to support a decision. Depending on the prediction and the decision-specific case, this may or may not be an issue. Now, when we do history matching, we confront the model outputs with real-world data. Essentially, we get rid of parameters which are unable to replicate measured data. The outcomes of this are a posterior probability distribution of parameters, which are all in agreement with observed data or that have an acceptable fit with that data. Now, if we populate our model with samples of the posterior parameter probability distribution and make a prediction, we obtain the prediction's posterior probability distribution. If history matching was useful, this posterior should be smaller than the prior, reflecting the reduced uncertainty. Now, what is evident from this is that history matching does not eliminate uncertainty. It can at best reduce the uncertainty of a model prediction. Now, also keep in mind that those uncertainties may still be very high. So where does calibration fit in here? As we have said earlier, calibration is the search for a unique parameter set which explains the data. This is in direct contradiction to Bayes' equation. However, we can seek uniqueness in a special way. The special way is to seek the parameter set which allows us to fit the data, but that also deviates the least amount from our prior knowledge. So effectively only changing parameter combinations where they must change in order to fit the data, but leaving other parameters that do not need to change alone. Conceptually, we are assigning an observation for every single parameter in our inverse problem, stating that unless there is information that contradicts it, these parameters or parameter combinations must have a specific value or relationship to other parameters. This unique parameter set is referred to as the parameter set of minimum error variance. Predictions made with this parameter set are not correct. They are at best the least likely to be wrong. So the parameter set for which the potential for predictive error is minimized. That is not to say that that error can't still be very, very large, merely that the prediction is expected to lie somewhere near the center of the posterior probability distribution. This is the parameter set which we seek during calibration. So calibration requires a well-posed problem. To make the inverse problem in a groundwater modeling context well-posed, we need some trickery, as we said before. The mathematical term for this trickery is known as regularization. Regularization can be broadly interpreted as any method that helps provide a meaningful answer from an ill-posed problem. In the past, to achieve a well-posed inverse problem, it used to be recommended to simply use less parameters. This was usually in the form of lumping them into spatially uniform zones and fixing insensitive parameters based on some expert judgment, thus reducing the number of unknown parameters in the parameter estimation process and constraining the inverse problem to become well posed. This is similar to what you may have done in the course assignment. However, although the idea of keeping it simple may be appealing, parameter parsimony introduces unquantifiable degrees of structural error to model predictions. These are often hard to detect and can have significant repercussions for the model prediction. This is a form of what is called manual regularization. Adding piecewise constant zones, for example, creates boundaries where properties change abruptly, do not follow geologically realistic patterns. These zones will have been delineated based on subjective choices by the modeler, and too few zones decrease the ability of observations to actually inform parameter estimation, which, as we've said, can result in model prediction bias. Such parameterization schemes may result in good fits with observed data. However, their parameter values are effectively very coarse surrogates for the complexity of the real world. Perhaps most importantly, by using few parameters, predictive uncertainty is often underrepresented. Fortunately, that type of approach is now a thing of the past. Advances in easy access to computing power, numerical solution techniques, and techniques for formulating the automated parameter estimation problem have made the use of highly parameterized approaches easily accessible. These approaches embrace the fact that there are many more unknown parameters than known observations, and that for a model to be able to reflect the uncertainties in these parameters, they must be accounted for. Having more and more flexible spatial distributions of parameters has the added advantage that it leaves room open for surprises, allowing for the potential for heterogeneity to arise in unexpected places within our model domain, where this heterogeneity is required to replicate system behavior. So, as I've mentioned, using lots of parameters gives us the ability to analyze the uncertainties made by a model, reducing the propensity for some structural bias. Now, even though we have many more parameters, many of which may be inestimable through history matching, these inestimable parameters are just as important as the estimable ones when characterizing the predictive uncertainty. So having many parameters allows us to capture as much information as is available in our observation data, whilst at the same time allowing us to characterize the impact of all that we don't know on our prediction of interest. Having many parameters does come at a cost. When using derivative-based methods, such as are implemented in PEST and in PEST++ GLM, the computational cost of calibration is proportional to the number of adjustable parameters. Operation of these methods requires carrying out a model run for every adjustable parameter during each iteration of the inversion process. Thus, available computational resources place a hard limit on the practical amount of parameters that we can include. Just to note, other history matching methods, such as the iterative ensemble smoother implemented in PEST++ IES, are not limited by parameter count, and can easily handle massive amounts of parameters without accruing additional computational burden. We'll discuss this later on. To constrain the number of parameters, a parameterization device named pilot points is often employed. When using pilot points, parameter values are estimated for a given point in space or time, so the pilot point. Values are then interpolated between these pilot points, and that interpolated field is assigned to the model grid. This allows for varying parameter fields with a lower amount of adjustable parameters than, for example, all of the cells in the model, but once again increasing the amount of heterogeneity which can be represented through parameters in the model. Once again, there is a great video by John discussing pilot points and tools on how to apply them, as well as some tutorials which take you through the basics, are available on the GMDSI website. Regardless of the parameterization device that we use, to undertake calibration we still need to identify combinations of parameters which are uniquely estimable given the data we have, and we need a mechanism through which to express expert knowledge to those combinations which are not uniquely estimable, for which we use singular value decomposition and Tikhonov regularization respectively. When attempting to history match a model with a large number of parameters, some of these parameters will be insensitive, meaning that changes to them have no effect on improving the fit between model outputs and measured data. Other groups of parameters may be highly correlated between themselves, meaning that the effect of changing one can be offset by a corresponding change to another. The classic example is the combination of recharge and transmissivity when simulating heads under steady state. As these two parameters are directly proportional, any increase in recharge, for example, can be offset by a corresponding increase in transmissivity to obtain the same value of head. In such cases, at best, the ratio of those parameters can be estimated, but not the absolute values themselves. All of these parameters are what is known as not identifiable. Combinations of these inestimable parameters reside in what is referred to as the null space. Combinations of parameters which are informed by observations reside in the solution space. Although, to make this picture a bit more realistic, in groundwater modeling, the null space is often much larger than the solution space. Singular value decomposition is a tool which automates the estimation of which combinations of parameters fit in the solution or in the null spaces. Parameter estimation-based SVD, so singular value decomposition, fixes initial values of insensitive parameter combinations and does not use them in the parameter estimation process. Thus, only parameter combinations which are estimable are used in the parameter estimation process, and thus the solution to the inverse problem becomes unique and solvable. Software such as PEST and PEST++ implement SVD during parameter estimation, as well as in linear uncertainty analysis tools, which we'll discuss in another video. From a practical perspective, when using these codes, SVD can almost become a bit of a set it and forget it kind of thing, with the magic happening in the background and without requiring much user intervention. Again, John has a video in which SVD is discussed in a lot more depth, which I recommend you watch if you wish to become more familiar with the underlying theory. Tikhonov regularization is a formal expression of soft knowledge into the calibration process by adding a second term to the objective function. This second term represents a penalty incurred if parameters diverge from some preferred condition. This preferred condition encapsulates the information which the modeler considers to represent the most likely conditions to exist. Usually preferred conditions are expressed as preferred values or preferred differences between parameter values. This provides a fallback position for these parameter values or relationships between parameters, and carefully constructed Tikhonov regularization can also introduce expert knowledge on the nature, disposition, and anisotropy associated with geological structures that may be reflected in calibrated parameter fields. This strategy ensures that where heterogeneity is introduced, it is introduced in a geologically meaningful manner, spreading heterogeneity over an area rather than attributing it to a single parameter. How strongly the soft knowledge constraints are applied is controlled by the weight associated to the regularization constraints. When using PEST in practice, weighting is usually handled automatically in the background, with the user specifying a target objective function. As the total objective function approaches this target, weights of the prior information are increased, thereby enforcing the soft knowledge more strongly. The target objective function should ideally represent the minimum possible misfit given the observation data uncertainty. In practice, this is rarely achievable or even knowable beforehand. Pragmatically, what is usually done is to set a very low target objective function calibrate, so essentially assigning very little weight to the prior knowledge. From that calibration, you determine the best possible fit you are likely to achieve with the model, and then you assign a target objective function which is slightly higher, usually 5 or 10%, and then repeating the process. This will usually result in almost as good a fit with more reasonable parameter sets, closer to or with a greater respect for your prior information or your soft knowledge. Once again, on the GMDSI website, there is a comprehensive video by John which goes into all the maths behind Tikhonov Regularisation, and which will provide a much deeper understanding of the intricacies of the method. There is also a tutorial on groundwater model calibration, which has a chapter dedicated to taking you through the steps of how to implement it using PEST. And all of this may sound very complicated, but actually putting into practice is relatively simple, as all of these tools have been developed and prepared, allowing the user to implement them without too much effort. And again, as I've mentioned previously, most good groundwater modeling GUIs will have tools to facilitate setup of these things for PEST. So, as we have seen, the objective function provides a single numerical value which encapsulates the model's ability to fit target values, prioritized according to the modeler's specifications, as well as soft knowledge. Parameter estimation implements methods of finding parameter sets which reduce this value until it reaches a minimum or acceptable level. This is conceptually accomplished by changing parameter values, seeing which changes reduce the objective function, and repeating. In practice, it's a bit more complicated than that. Imagine a case in which we have two parameters. Combinations of these parameters result in different values of the objective function. We can plot the surface of the objective function as a contour map, such as is shown on the slide. So in this case, we have two parameters. For any case in which the combination of parameter 1 and parameter 2 in the model result in an objective function that have a value that falls along this line, all have the same objective function, and so on and so on. So in this case, each concentric line represents an isoline of the objective function value, which decreases as we progress to the center. To find that minimum, a parameter estimation code will perform a series of model runs, each with different parameter values. For example, in such a case, a model would be run once with initial values, and then run again once for each of the adjustable parameters, adjusting each of those parameters by a small amount. By comparing the effect of parameter changes on the change in objective function, the parameter estimation code calculates the slope of the objective function surface, so that contour map there that we're looking at, and from that slope it can determine the direction in parameter space to take in order to head towards that minimum value of the objective function. Now, because groundwater models, the responses of observations to parameter changes are usually non-linear, the search for optimal parameters must accommodate this non-linearity. So rather than having that nice smooth contour field, we'll actually have this blobby, disformed thing which does not have a clear direction towards the minimum. A widely used method, and the method which is applied in PEST and PEST++ GLM, is based on the derivative-based Gauss-Liebenberg-Marquardt method, or the GLM method. Observation to parameter derivatives relate the change in simulated value of the target to a change in the value of a parameter. These are referred to as a sensitivity or parameter coefficients. The set of sensitivity coefficients for all parameters and observations in a history matching problem form a two-dimensional matrix referred to as the Jacobian matrix. To obtain all the sensitivities to fill a Jacobian matrix, a model needs to be run as many times as there are adjustable parameters, plus 1. Once that Jacobian has been filled, the slope of the objective function surface in the parameter space vicinity is used to determine in which direction to adjust parameters to improve the fit. New parameters are then selected, and the process is repeated, refilling the Jacobian, finding their direction, and updating parameters. Each of these steps is referred to as a parameter estimation iteration. The process continues until a modeler-imposed criteria is met, usually when the improvement in fit between iterations is less than some percentage, or if the modeler deems the fit is good enough. Again, a video in which I've actually linked to before goes into these concepts in a lot more depth and mathematical rigor. Now, as you can see, this process can become quite costly in terms of computation time, and it scales proportionally to the number of parameters being estimated. This imposes a ceiling on the practical number of parameters that we can include in a parameter estimation process. And as we saw earlier, and as we'll see in the subsequent video on uncertainty, using too few parameters brings a risk of incurring predictive bias and underrepresenting uncertainty. So we want to have as many parameters as possible. However, we are limited by the computational resources and the cost in terms of time required to estimate them. Again, as mentioned earlier, one approach to minimizing this cost is to reduce the number of adjustable parameters using parameterization devices such as pilot points. Thus, instead of attempting to estimate the values for all model cells, we can reduce them to a manageable number of pilot points, while still retaining the ability to express heterogeneity. Of course, the ease of access nowadays to parallelized computing, whether through local networks or in a cloud, allows many model runs to be carried out in parallel, speeding up this process significantly. In practice, a modeler needs to design a parameterization scheme accounting for the resources at their disposal and the runtime of their model. This is a strong argument for keeping models fast and nimble, as what is the point of having a very highly detailed model with lots of cells, which looks as close to a picture of reality as we can make it, if we cannot use this model to extract as much information as possible from data in order to inform a decision. But I digress. We will revisit the topic of appropriate model complexity in the next lecture. It is worthy of note that relatively recent advances in the use of randomized and ensemble methods, such as are implemented in the iterative ensemble smoother used by PEST ++ IES, provide efficient approximations of the Jacobian matrix at a fraction of the computational cost. Most importantly, as the number of runs for these methods required to approximate this matrix is independent to the number of parameters, the ceiling to the practical number of parameters is lifted, drastically reducing the potential for predictive bias. When using things such as IES, often only a few hundred model runs are required per iteration, coming in at a fraction of the computational cost. Of course, as with anything good in life, there is always a caveat, and in this case the cost is that the Jacobian matrix filled using these methods, which is referred to as often as a rank deficient Jacobian matrix, is unsuitable for applying linear uncertainty analysis tools, which we'll talk about in the second lecture, as well as that they often do not achieve quite as good a fit, especially in highly nonlinear problems. So you may be asking why we should care about obtaining this unique parameter field, and why not go straight to sampling all the possible parameter sets which can fit the data, so as to characterize our prediction posterior probability distribution. And what does it actually matter to be there in the center of that probability distribution? Perhaps one of the most useful outcomes of calibration is actually to gain insight as part of the model development process, as it allows us to see the parameter heterogeneity which must exist to explain the data that we have. This can often have a very didactic value, throwing up unexpected surprises or providing insight into structures or processes which we would otherwise have ignored or been unaware of. It becomes much easier to see this if we're looking at a single parameter field rather than trying to explore all the possible or many possible parameter fields. Secondly, this calibrated parameter set will usually be obtained using a derivative-based method, as we just talked about. This opens the opportunity to apply a suite of linear analysis tools which can analyze the flow of information from data to parameters and predictions. These can provide relatively cheap but quite powerful tools to assess uncertainty, as well as to explore things such as data worth of potential as of yet unavailable new data, and can be quite a powerful tool to help design, to prioritize what new data to collect to reduce the uncertainty of some model prediction. Again, we'll discuss these tools more in the second lecture. So, to summarize, we've seen that the goal of modeling is to make a prediction and quantify the uncertainty of that prediction. It's important that models are designed to facilitate this and not designed thinking of them as simulators of a system or of some picture-perfect representation of an environmental or groundwater body or groundwater system. We must always accept that there will always be uncertainty. History matching allows us to reduce that uncertainty, but it will always be there. We've also seen that more parameter flexibility reduces the propensity for uncertainty to be underrepresented, which we will demonstrate more in the second lecture, and highlighted that calibration is different from history matching in that calibration finds the solution of minimum error variance, which expresses the best fit with hard and soft data. However, it's important to remember that a calibrated model should never be an end goal. History matching is only a step along the way towards assessing a model's predictive uncertainty. The end goal of decision support modeling is actually to provide the confidence intervals around that prediction for which the model is being built. So always keep in mind that history matching and particularly calibration are only a step along the way. They are not the end goal. Now that has been a very high level overview. I do strongly recommend that you dive into the other videos that I've linked to, as well as read some of the material which you'll find on the GMDSI website, as well as on the PEST homepages and so on. Learning of all of these tools can take a while, but they are definitely necessary in order to undertake modeling with a scientifically defensible approach to solve real-world problems. Perhaps a gentle introduction to using PEST and PEST++ is to actually use groundwater modeling GUIs and follow their tutorials where they have them for using PEST. At the time of recording this video, the implementation of interface into the free GUI ModelMuse is still in development. However, do keep an eye out for a new release in the near future in which ModelMuse should be able to, or will be able to support an interface with PEST. However, using the GUIs will always be somewhat limited. You will learn a lot more by actually getting your hands dirty with configuring PEST and PEST++, etc. Directly. The GMDSI tutorials will take you into what happens in the background, so they'll show you the files and how to interact with them and explain what's going on. This is quite important if you wish to apply these types of software beyond the bounds imposed by most GUIs, and given the complex and often unique types of problems that we face when building groundwater models, not being able to do so can be quite a limitation. If you are comfortable with Python, I do recommend looking into the PyEmu module. PyEmu provides a Python interface to PEST and PEST++ especially. Apart from that, I would highly recommend, if you are not a Python user or coder in general, I would highly recommend gaining these skills if you wish to, or to invest in becoming a groundwater modeler. Although you don't have to, they will open up a lot of doors, as they have the advantage of becoming much more able to customize your setups, as well as script your workflows, and thus reducing the mental overhead required to remember where all the moving pieces are, and of course making the whole process a lot more reproducible and transparent. So to become familiar with PEST and PEST++, as well as to learn how to apply all the things we've spoken about here today, I recommend starting with the GMDSI tutorials. These take you through the details of how to configure, run and interpret the outcomes of PEST and several of its utilities. It's hard to recommend a unique starting point, as various of the concepts weave together to create a whole. Perhaps the most useful would be to start with the tutorial on calibration, as this will provide the most generalizable concepts, I think. From here, you may want to move into tutorials on parameterization, so to understand how pilot points work as parameterization devices, and how to specify covariance matrices, which are used to express prior knowledge of geological heterogeneity. From there, you may wish to go through the tutorial on OLPROC, which demonstrates the use of a utility to post-process model outputs into secondary observation types, amongst a few other things. And these tutorials should give you the core understanding of how to use PEST in a calibration context, as well as providing the basis or the fundamental knowledge that you're going to need in the subsequent steps in which we apply many of these tools and software into continuing the uncertainty analysis of a groundwater model. So in the next lecture, we are actually going to address other PEST utilities as well as the PEST++ suite in the context of uncertainty quantification. Now I'd just like to leave you with this phrase. Always remember that there is no such thing as safety or certainty, only degrees of uncertainty or risk. See you soon.